Fast. I'll be ending the quiz in 5, 4, 3, 2, and 1. The correct answer is electromagnetic radiation because it was radio frequency which helped a lot in getting that image. So our next question. Identify this. What it is. Fast. I'll be ending the quiz in 5, 4, 3, 2. Yep. The correct answer is it's a radio telescope. So that network, mesh-like network, it resembles radio telescopes mostly. That's why. Next question. Okay, very easy. Listen. So I'll be stopping the quiz, ending the question in 1, 5, 4, 3. Yeah, all done. So I think somebody joined newly. So you can go to the link and enter the code which is in the chat box. I think Adesh, you can repaste the link. So go to the link and add this code, which you can see 872085. Then even you can be able to practice in. You can participate. The next question. It's pretty easy. I'll be ending the quiz in 5, 4, 3, 2, and 1. So that is the emission spectral lines. So let us see leaderboard now. So we have Priyavarshini, Aryan, Kirti, random 1, 2, 3. Okay. So we have the next question. So one guy partially answer. I'll be stopping the quiz. Yep. All done. So it's slightly confusing question. The correct answer is cosmic rays because cosmic rays contain these protons, neutrons, and the nuclei of atoms, right? Charged particles. So most of the cosmic rays will be that particles. So they can be divided. They are not fundamental. But neutrinos are fundamental. Electromagnetic waves have photons. They are fundamental. And even gravitational waves, we have a theory called gravitons by string theory. So gravitons are also fundamental, but not cosmic rays. Okay, 5 seconds remaining. Yeah, yeah, everybody answered. The correct answer is transverse quadrupolar. Why transverse? Because in the image itself, you can see the uh, how the particles are vibrating, right? They're vibrating perpendicular to the direction of the wave. So they are transverse, and it's a quadrupolar wave. By linearist theory of gravity, we get it to be quadrupolar in nature. Five seconds remaining. Okay. So the correct answer is superposition as well as interference. Now, why superposition? Because yeah, so you can see the board. So why superposition? Because it is superposition of incoming, that is the emitting and reflecting wave. That's what causes the interference and then detected by the photo detector. So next question. 10 seconds remaining. Fast. Okay. The correct answer is spiraling phase, then merger, and then you can see the leaderboard, Priyadarshini, Kirti, Aryan. So then last is ring down phase. I'll be ending the question in 5, 4, 3, 2, and fast I'll be ending it. It's very so the time's up. So the correct answer is stochastic and burst gravitational waves. So we see leaderboard, we have Priyadarshini, Kirti, Aryan, who's random. So the correct answer is the time is over. So leaderboard we have Kirti, Priyavarshini, Aryan, Kush, and Meva. The correct answer is neutrinos. And moreover, that will be our third week problem, if you consider. So time's up. The correct answer is all the neutrinos, muon, electron, and tau neutrino. All these three are antiparticles and their charge both to be zero. So 5 seconds remaining. Okay. So we have Kirti, Priyavarshini, Aryan, and Kushal. So we completed half of our quiz and still half quiz is remaining. It's pretty easy. I'll be ending the question in 5, 4, 3, 2, and firstly, who didn't answer? Answer fast. I'll be ending it soon. Don't try to Google. Okay. So the correct answer is muon neutrino because it has the large penetration power. Okay. Kirti, Aryan, Priyavarshini, Kushal, random. Last 5 seconds. So the correct answer is 1. They don't have charge. Okay, let's see leaderboard. Kirti, Priyavarshini, and Aryan. And Vaishnavi came to top 5. Yeah. So the correct answer is 1. They don't have charge, and another they participate only through weak interactions, which is very short ranged. So that is the main reason. Last 10 seconds remaining. It's a pretty tough question. Let me give answer time. So who didn't answer? Please answer fast. I'll be ending the question in 5, 4, 3, 2, and 1. Okay. The correct answer is, let's see the leaderboard first. No leaderboard. Okay. The correct answer is beta minus and neutron decay, and it's the last equation. All three are correct. Last 5 seconds remaining. Okay. Time's up. So leaderboard we have Aryan, Priyavarshini, Kirti, Kushal, and Boos. Okay. The correct answer is Super Cameo Kande. Last 10 seconds. Okay, time's up. Leaderboard Aryan, Kirti, Priyavarshini, and Boos. Okay. Our next question. So it's pretty confusing and but yet easy. I'll be ending the question in 5, 4, 3, 2. Fast, I'll be ending the question. Okay. The correct answer is protium nuclei. Now, what is protium nuclei? It is a proton. So, proton is the most abundant cosmic ray particle. Like 90% will be proton. I'll be ending the question in like 5 seconds. 5, 4, 3, 2, and 1. So the correct answer is both atmosphere and magnetic field. Yeah. The leaderboard is the same. Last 10 seconds. And these are last question for now. So we have leaderboard. So I think we can stop a quiz because the coming quizzes are all about not required, and we have 10 constraint. So, yep. So how was the quiz, guys? So let us see leaderboard if we can. Okay. So first is Aryan, Kirti, and then Priyavarshini. Congrats.
How many questions did you do?
Like 25 questions.
Wow, nice. Okay. Cool. I hope people who did not get the chance to attend it last time were able to attend it today.
Yeah. Let me download it because we can go through in future.
Yeah. Do you want me to make another announcement to the neutrinos group? Because I don't think all of them have joined.
Yeah.
So, okay.
Okay, guys. So let us go to our presentation today. I can take a like 2 minutes break now. Like after 2 minutes, we can start, right?
Yeah. Just take a 2-minute break. I think some more people might join now. So let's just give them
Are all people here? Like Aratha, Shobit, Samruddhi, and Vishak? You'll be presenting today.
I'm there.
Yeah, I'm here.
Yeah, I'm here.
Okay.
Yeah.
I didn't apply for presenting. I just submitted it.
Who is that?
Saikam sir.
Okay. So shall we start now? If all are here.
Yeah.
Okay.
Yeah, I think
So, Jivan, will you record the session?
it's being recorded.
Okay. So now we are entering to our second day in our neutrino presentation. That is particle and astrophysics, astroparticle physics. So it's a basic overview. So now, if we want to understand these particles, what are these particles, their nature, we should know one concept. That is, what is meant by fundamental? What is actually fundamental? So if we consider our matter, it is made up of minute divisions. We can divide them further and further as we magnify. We can make it divide them to crystals. We can find atoms. That is, if we divide the crystals, we'll get atoms. In this scale, like in 10 power minus 10 meters, in that order, atoms will be. If we still divide them, like if we go deeper, we can see the atomic nucleus. Now you can see atom is not a correct depiction. Actually, it is like it will be central nucleus, and then have this surrounding orbitals, s orbital, and all these orbitals. So nobody knows how the correct atom looks like, but we have a rough idea how it might look. So this is how atom is. If we go deep into the atom, like if we consider a nucleus, so even atom can be divided. So if we go into the nucleus like this, so we can see the atomic nucleus consisting of protons and neutrons. So even atomic nucleus can be divided to nucleons. So these nucleons are nothing but protons or neutrons as such. So even these nucleons, we can divide them further. There are some particles called as quarks. So quarks are present in nucleons. If you consider this to be a neutron, you can see three types of quarks in them. That is a down quark, another down quark, and an up quark. So you can see these types of quarks. And moreover, the range, that is the order of these nucleon, is 10 power minus 15 meters. At a very minute scale, we can see nucleons. Then who knows how small these quarks can be? Can we define a size to these quarks? So we all get the answer in the next topic, that is the properties of fundamental particles. So any particles will have something called as properties. Anything, any topic we say, any concept, first we'll go to the properties, because properties helps us to understand those particles in very good manner. So first property is generally we can say mass. So mass is a property of a particle. Any particle can have mass. Mass can be zero or some non-zero mass, but it has some concept called mass. Now we have a theory called as gauge theory. Now what does this gauge theory tells us? Gauge theory, it gives some conservation laws and some transformations, some rules applied, gauge invariance. So many such concepts are present in gauge theory, which will describe some particles or some properties of a particle. So those properties are nothing but like charge, and we have color, we have like flavor, we have quantum numbers. So all these quantum numbers are associated with flavors. And we have something called as chirality. And we also have something called generation. So all these concepts is got by gauge theory. So gauge theory theorizes all these concepts. Now charge is a property that is It's a property of a particle. Even color, we define something called as color, flavor, chirality, quantum numbers, generations for particles. Now we have all this for different particles, it will be different values. So these values define a particle actually. Now we have another property called as spin. Now spin resides in the quantum nature of a particle, the quantum nature. Now de Broglie's equation, it relates how the momentum of a particle, that is the particle property, is related to the wave property, right? That is P is equals to h by lambda. It's also nothing but h bar by k, where k is the wave number of the wave nature of particle. Now using this momentum, we can also define a property called as angular momentum. So angular momentum. So angular momentum is an intrinsic property. We can't see now angular momentum. Classically, we can say any spinning object. So if you have any ball, if it is spinning, we can define an angular momentum to the ball, and we can say it is spinning in one direction or something. We can tell. But for particles, like minute particles, like fundamental particles, we can't assume them to be spinning. So we can't tell they are spinning actually. Rather, it is an intrinsic property of the particle. The spin of a particle is an intrinsic property. Now we can know this formula called as angular momentum quantum number, that is denoted by L. So now L is given to be h bar square root of s plus s into s plus 1. So this is nothing but which defines angular momentum of a particle, where L is the angular momentum quantum number, h is the reduced Planck's constant, s is nothing but the spin number. So s can take values like 0, 1 by 2, 1, minus 1 by 2, minus 1, such that it can take any values. S can take any values. So based on different s values, which we call it to be spin. So the s is nothing but the spin of a particle, the spin quantum number. It defines the angular momentum of that particle. Now the spin and angular momentum are intrinsic nature of that particle. Okay. So now if we know such fundamental particles properties, the standard model, which we'll see in further slides, it describes some types of particles, like some classes or some like families of particles, which have some interrelatable properties. Like you can see, this is nothing but quarks. So these are the quark family. In quark family, you can see two rows. So there is one row here and another row here. So this is another row. So the top row is called as up-type quark. Up-type quarks, and the bottom row, what you see, is called as down-type quarks. Now these up-type quarks have three types of particles. That is the up quark, the charm quark, and the top quark. We have three types of up-type quarks. Now down type, we have down quark, strange quark, and we have bottom quark. So totally there are 6 types of quarks, right? So these 6 types of quarks are called as flavors. So how many flavors of quarks are there? There are 6 flavors of quarks. Now even these quarks have a property called as charge. These quarks have non-zero charge. So what is the charge? That is, all these up-type quarks have plus 2 by 3 charge, and down-type quarks have minus 1 by 3 charge. So charge is equals to plus 2 by 3 for up-type, and charge is equals to minus 1 by 3 for down-type quarks. And quarks generally have spin is equals to 1 by 2. Their spin quantum number is 1 by 2. Now these half integer spins have a different name, which will be explaining towards the end. So the spin is 1/2 for now. Now they have something called as color. There's something called as color. There are 6 colors of quark. That means if you consider up quark, there are 6 colored up quarks. If you consider down quark, there are 6 colored down quarks. Now color is nothing but something arising from quantum chromodynamics. They say color to be a charge, some different type of charge called as color charge. So it defines the color of the quark. So color means it's not mean like red color, blue color, not such type of color. Rather, it is an intrinsic property. Like charge is an intrinsic property, spin is an intrinsic property. Now we can see what are the forces interacting with quarks. Now we know 4 types of forces, right? We know strong force, we know weak force, we know electromagnetic force, and we also know gravitational force, gravity. So these quarks interact with all the forces. So quark will interact with strong force, quark will interact with weak force, quark will interact with electromagnetic force, and quark will interact with gravitational force. So all the forces can be, they can interact with all forces, and mainly they interact with strong force. One of the most important property or interaction is the strong interactions between the quarks. So why strong interaction? You'll come to know in the bosons concept. I'll explain that detailing in bosons. So now you got a fair idea of quarks, right? How many quarks are there? What types of quarks are there? So let me go to the next concept, that is the leptons. So even in leptons, we have 6 types of leptons. We have electron, muon, tauon, electron neutrino, muon neutrino, and tau neutrino. Now these top row, what you see, all are charged leptons. They are charged, but these are neutral. So they don't have charge. Moreover, we can tell something called as the this color charge, what we told in quarks, they are not in leptons. So leptons don't have color. So no color for leptons. There's no color. And moreover, there are 6 flavors of leptons. Now, what are these 6 flavors? They're nothing but these. Electron is a flavor, muon is a flavor, tau is a flavor. So similarly, all these are something called as flavors of leptons. Now, you can see these neutrinos, right? Are one of the our interest in our project is neutrinos. So if you consider neutrinos, charge of electron neutrino, muon neutrino, and tau neutrino is 0. Charge is equals to 0. Moreover, they interact only through weak force. Only weak interactions they have. So neutrinos have only weak interactions. But other leptons like electron, muon, and tauon, that is the charged leptons, so they have interaction with weak force. Now, since they have charge, they also interact with electromagnetic force. Now, since they have mass, they interact with gravitational force. Now, one thing you have to notice is the gravitational interaction is very, very negligible when compared to electric and weak force. Because we know gravity is the weakest force, and because of that, they interact very less. They have interaction, but that is very, very negligible. So these are the interactions of charged leptons. Now, uncharged leptons, that is the neutral leptons, we can tell that they have charge is equals to 0, and they have interaction only through weak force. Now, if you consider the antiparticles, that is the antiparticles of neutrons, we have something called electron antineutrino, muon antineutrino, and tauan antineutrino. So these are antineutrinos of our known neutrinos. Now, how would they differ is they don't have charge. This has charge 0, even they have charge 0. Then how do they differ? You have to know, right? So that is got by some property called as chirality. So they have different chirality. What is that? These neutrinos, where we can say normal or not an antiparticle, rather normal matter, such neutrinos are left-handed. They have left-handed properties, and these antiparticles have right-handed properties. So chirality will be different. So because of that reason, we can differ the antineutrino and neutrinos. And moreover, their lepton numbers, which we'll be covering in us first week, the flavor quantum numbers. So there will become to know they have different lepton numbers and such. So now you understood our leptons, right? What are the properties of leptons? Now we'll go to the
Excuse
boson.
me.
Yeah.
My question is, what is the what do you mean by left and right-handed? That chirality you are explaining. Can you explain again?
Okay, chirality is a property of a particle, right? Now we can tell chirality of a molecule. You know, any molecule has chirality. If it is chiral molecule, we can tell left-handed molecule, right-handed molecule. Similarly, these particles have something called as intrinsic chirality got by this gauge theory. So gauge theory is the basis of all this nature, what we are dealing now. So gauge theory theorizes this chirality property also. So we can tell they don't have, okay, they differ in chirality. Okay.
Sagar, can I?
Yeah.
I'm really sorry to interrupt. But can I just make it a little more simpler without involving gauge theories and so on?
Okay.
So chirality is sort of this symmetrical thing that you're looking at, and it sort of tells you about the mirror image of whatever it is you're looking at, right? So it's like if the mirror image is the same as your original object, then you give it some sort of chirality, and if it isn't, then you cannot say that they're the same things. So if you're telling that the neutrino has left-handed chirality, it means that if you were to take a mirror image of it, even in the conventional sense, if you were to put it in front of a mirror, you won't get the exact same thing. You see that it would be rotated or something. It's like how your right and left gets interchanged when you look at yourself in a mirror. That's all chirality is in simplest terms. I hope that makes it a bit more clear without involving gauge theories and so on.
Okay, means we generally say it is a mirror image of the
Kind
particle.
of, yeah. Vaguely, yes. That's how you can look at it. I mean, it's not exactly that, but that helps us understand what exactly chirality is all about. And this is something that you also observe in chemistry. So, although chemistry people, if you've read about glucose molecules, you see that they have some sort of chirality, right? They produce phase shifts and so on, but it has to do with the chirality of all those things. So, yeah. Sorry to interrupt, Sagar.
Yeah, no, we can. Thank you.
Can I make an addition for that?
Yeah, sure, definitely.
What I was thinking is that suppose if you talk about a spin of electron or whatever we talk about in a general sense in quantum mechanics, spin is an intrinsic property of the particle. Like we generally do not observe spin, but it's an when we make it to pass through a external magnetic field, we observe two spin direction. So it's an intrinsic property. We just named it as a spin. Similarly, I was thinking that chirality, yeah, the actual literal meaning is about the mirror image and stuff, but I feel that this chirality is this intrinsic property of that particle, which kind of it aligns itself towards some left or right so that we can differentiate it. But it's not in the literal sense that we can take about the mirror image, that kind of analogy.
Yeah, absolutely. You're absolutely correct. I didn't want to bring in spin and stuff. So the simplest way you look at it is assuming that you can take a mirror image of it. But yes, that's how you observe.
Another way, if for the uninitiated, I would like to say is that it's just that these properties, they kind of align itself to some other external force, will be a wrong word to use, but some external effect. if we keep some external effect, these particles, they kind of distinguish in such a way that they give us some completely separate entities. So if at all we are talking about here, I cannot comment about this neutrino because I'm new to this stuff. But in this way, this chirality, the left and right, they kind of they distinguish themselves completely separately, left and right, under the forces, fundamental forces that we are about to go on. So in that way, we can think about chirality, I guess.
Yeah, Abhishek. Yeah, you are right. Okay. So anything to add, Vikrant? Or should I continue?
No, you can proceed.
Okay. So now if we come to know about leptons, we have another category called as the bosons. So bosons. Now bosons have a one thing. If you remember bosons, first thing is the spin change. What we see, that is initially in the previous two categories we saw spin is equals to 1/2, but here we have spin is equals to 1. So all these bosons mentioned here, we have the photon, the W boson, the W plus, the W minus boson, and Z boson, and gluon. All these bosons, we can call them as gauge bosons. They have a name called as gauge bosons. Now all the gauge bosons have something spin called as, their spin is 1, where they are the force carriers. They're the force carriers. We said the four forces, right? The gravitational force, fundamental forces, the gravity, weak nuclear force, strong nuclear force, and electromagnetic force. So for three forces, that is the EM, the electromagnetic force, we have a force carrier particle called as photon. That is this photon. And we have for weak forces, the force carrier particles are W bosons. That is, we have W minus, W plus, and W, the neutral one. And then we also have something called as Z boson. That is neutral Z boson. Now, photon has charge 0, and W bosons have three types. That is the W minus with minus charge, W plus with plus charge. These two are antiparticles of each other, and W0 with a neutral charge. And Z is also a boson that mediates the weak force, that's also neutral. Now we have another force, that is a strong force. This is mediated by a boson called as gluon, denoted here G. Now in all these forces, in all these force carrier particles, what we call, they're called as gauge bosons. And moreover, they can affect the particles, like they can accelerate the particles. They can accelerate the particles. And they have something called as mass. Now only these W bosons, these weak forces, only these have mass, some non-zero mass. So weak forces bosons has non-zero mass, and electromagnetic force, right? Here the photon, we know mass of photon is 0. And strong or gluon, even that gluon particle has mass is equals to 0. So we came to know the mass of them. Now we have to know the color. Now in all these three particles, there is three types of mediating particles. Only strong force, that is the gluon, has something called as color. There are 8 color charges, 8 color charges for gluon. Now since 8 color charges are there for gluon, and even we saw quarks have colors, only because of that nature, we can tell quarks interact with gluons, that is a strong force, and leptons, which doesn't have color charge, doesn't interact with gluon, that is a strong force. So now did you understand about the bosons? So they are the force carrier particles. Now we came to know about the 3 types of force carrier particles, that is weak, electromagnetic, and strong force. Now there is some other boson called as the Higgs boson. Now it was a controversial topic in sometimes, like in before some years, It's a controversial topic, but now we discovered Higgs boson and named it as God particle and whatnot. So that has mass, which is not approximately, we can tell approximate mass to be 126 GeV by c square. It has mass, and the nature is it's not a gauge boson, rather it is something called a scalar boson. Its spin is 0, and it is not a force carrier particle. It's not force carrier. So why it is not, and since it is not force carrier, it is not a gauge boson, rather it is a scalar boson. It cannot interact with particles and have a force. It can't impart a force on the particles. Rather, it will give something called as mass. Now, what is that mass is? In quantum field theory, the quantum field theory theorizes a field called as Higgs field, and the quantized particle of Higgs field is Higgs boson. Now, that Higgs boson, what it does is, it interacts with particles which have mass and actually gives the mass. So now, if Higgs boson, if it interacts, if Higgs boson interacts with up quark simply, then it gives its mass. So actually, I don't know much about Higgs boson. Rather, simply not to leave it, I just explained this. So this is about Higgs boson. It gives mass to the particle. Now, if we consider all these families of boson, all these families of particles like the quarks, the leptons, the gauge bosons, and Higgs boson, we get something called as the standard model. The standard model. So the standard model image, this is the image of a standard model which comprises all the known detected, experimentally detected particles. So we have quarks, leptons, and bosons. All these are experimentally detected particles. So they are proved to exist. Now the first row, what you see here, now this first row, what you see, this is called as the first generation particles. First generation particles. The second row, what you see, the charm, strange, these leptons, they are called as second generation particles. And here, the third row, what you see, they are third generation particles. Now, all these particles, first generation, second generation, and third generation particles, make something called as fermions, whose all these particles in these fermionic particles, have spin to be 1/2. You can see the spins, right? Even spin is mentioned. So that is 1/2. But for these bosons, spin is integer spin. They have something called as integer spin. Now, why integer? Because their spin is 0 or 1. You can see the spin to be 1 here. All the gauge bosons have spin to be 1. But for Higgs boson, it is 0. So they have something called as integer spin. So this standard model image comprises all the known theorized and detected and experimentally proved particles. So if you want to differentiate this Higgs bosons and fermions, there is one simple differentiation what you can do. It is called as symmetric and antisymmetric nature of fermions and bosons. So what is this symmetric and antisymmetric nature of fermions and bosons? So now, by quantum mechanical concepts, actually you can theorize the wave function difference and the exchange symmetry, that's the quantum state symmetry, exchange of states. By all those topics, what you can do is you can differentiate bosons and fermions. I think my time is up. Even they have to produce. I think I can't complete this topic. Rather, I'll give the final to expression. I'll not be deriving it. Rather, I'll give the final to expression. So if you consider phi a and 1, if you consider a particle having this wave function, where a is a particle a with state 1 and phi a2, particle a with state 2. So if you consider these 4 particles, phi a1, phi a2, phi b1, phi b2. Now what you got? 2 particles with two states. If you consider this system of particles, if all these are interacting or and are in the same system, if these particles A and B are fermions, that is, if their spin is 1/2, if you consider their spin is 1/2, the total wave function is given by 1/√2 phi A1 phi B2 minus phi A2 phi B1. So this is the total fermionic wave function. This is the wave function of the system if the particles are fermions. Now, if the particles A and B are bosons with spin 1, if you consider the spin is to be 1, then the total wave function is given by the same equation, but the sign is minus here, but here it will be plus. So this is the total wave function if the particles are bosons. Now, if you consider these particles, so if you consider the system with fermions, what happens if the states are same? That is, if phi A and phi B, their state is 1 itself. If you consider the same state, what happens? Here it will be 1 and 1, here also it will be 1 and 1. So they'll be cancelled, right? If they're in the same state, what happens? They'll be cancelled. So you can cancel them if they're in the same state. Then phi F is equals to 0. Now, what does this phi F is equals to 0 mean? We can say phi F star also to be 0. Now, phi F star, phi F is equals to 0. Now, what does this give? It gives something called as probability of the state, right? If probability is 0, what does that mean? We can tell the probability of fermions to be having same state in the same system is 0. That's why we get a property called as a principle called as Pauli's exclusion principle, which states fermions with same state and can't exist in the same system. Okay, but what happens to bosons? Now, boson, since there is no plus, there's no minus sign, there is plus sign, that will be added, right? So then phi B is not equal to 0. So now we can tell bosons can exist in the same state in the same system. So that is the main difference between fermions and bosons. Okay. So I'll end my particle physics concept here. Now Aratha will be continuing with the astro-particle physics.
I'm having a doubt.
Yeah.
Yeah, we say neutrons and protons are all made up of quarks, and we know that one up quark and two down quarks make a neutron.
Yeah.
Are this we talking about up and down? These are type of the quark, or we are in the specific class that down we are having some strange bottom or down, which we are talking about. All neutrons same or they have different compositions of different quarks?
So you're telling there are some particle which instead of up and down, there are something called as strange, that type of quarks, that type of particle, right?
I think
No, I am
he's saying
saying
that
that
the same particle can it be made with different quarks with the equal to same charge, right? He's asking that.
Yeah, equal to same charge, we can make a particle. If you consider a particle called as some particle which have one tau, there is the one top quark, and we have I'm not knowing the correct value, but rather if we have two strange quarks, so now this charge will be nothing but 1, right? No, it will be 0. Now charge will be 0 for this particle. So I don't know if it can exist or not, because we haven't detected it. If it exists, it will be having a very short life. Even if it exists, it will have very short life. But this is having a very long life, right? This is a neutron, it has some 15 minutes of life until when down quarks will decay.
Then neutron is exactly made up of what?
Which
Which
is
type
a
of
neutron?
quark?
Neutron
It's
is made
made
up
up
of
of
this quark.
2 down and 1 up.
Yeah, this is neutron.
Okay.
If you consider proton, it has 2 up quark and 1 down quark. This is proton.
No, I am asking that you defined 6 quarks into 2 different classes, up and down.
Yeah.
Are these up and downs for neutron and proton? These are the classes or specific up quark or down quark?
Yeah, I understood. So U is up quark. Up type, it's not up type, it's up quark. And D is the down quark.
Okay, thanks.
Okay. So we'll go to the astro-particle physics now.
Am I audible?
Hi.
Yeah.
Okay, so I will start with the basic definition. So astroparticle physics, which is also called particle astrophysics, is actually a branch of particle physics which studies elementary particles which have astronomical origin and the relation to astrophysics and cosmology. It is actually a very new field of research, and it is emerging at the intersection of various fields of physics such as astronomy, astrophysics, relativity, solid state physics, cosmology, etc. Can you change the slide? Okay, so now the question arises how this branch came to be. It's actually a very interesting story. So it all started in 1910. Just a spoiler, we are going to discover cosmic rays. So a German physicist named Theodor Wolff measured ionization within air at the bottom and the top of the Eiffel Tower. He found that there was far more ionization at the top than what was expected if only terrestrial sources were to attribute it for this radiation. At sometime later, an Austrian physicist named Victor Francis Hess hypothesized that the ionization was caused by the radiation from the sky. So in order to prove it, he designed an instrument capable of operating at high altitudes and performed observation on ionization up to an altitude of 5.3 kilometers. Change the slide, please. So from 1911 to 1930, Hess made 10 flights. He measured ionization levels. So his measure revealed that although the ionization level initially decreased with altitude, they began to sharply rise at some point. At the peak of his flights, he found that the ionization levels were much greater than at the surface. So he concluded that the radiation of very high penetration power enters the atmosphere from above. Also, during one of the Hess flights, there was a total near eclipse of the sun. But at that time, he did not observe any dip in the ionization level. So Hess concluded that the source of the radiation has to be far away. In 1925, Robert Millikan confirmed Hess findings and subsequently coined the term cosmic rays. And after that, the Hess was awarded Nobel Prize in Physics for this discovery in 1936. Change the slide, please. So these are the images of the scientist Theodor Wolff, and the right one is Hess. Next slide, please. Yeah, this is an image of Vector Hess. Actually, he conducted all the 10 experiments, all the 10 flights in an air balloon, and these are all the physicists helping him out. It's interesting, I know. Next slide, please. Left image is the latest cosmic ray detectors, and the right graph is actually the graph that has drawn. So you can see that there is a dip at one point when the altitude increases, but after some point it increases continuously without any dip. Next slide. Yeah. So now the next thing that interests people is what are the active research area in this field of science? What are its future plans? And the interesting part is that there are some interesting problems need to be solved. So it actually covers many areas of physics, such as mentioned here, high energy, cosmic ray physics and astrophysics, particle cosmology, supernovas, active galactic nuclei, cosmic abundance, dark matter, high energy, gravitational wave, and etc. The next slide, please. The main task of it in the future is to define itself from its working definition. Actually, it doesn't have any textbook type definition. It's a mixture of various fields. So the scientists are trying to differentiate themselves from astrophysics and other related topics completely. And some of the major interesting unsolved problems I talked about are the characterization of the dark matter and the dark energy. And the second is, why is there more matter than antimatter? These problems are still unsolved. And you can see the image, it's actually simulation of the dark matter. Now my friends will be going deep in the multi-messenger part of the astrophysics, astroparticle physics. Samriddhi, please.
Excuse me.
Yes.
Yeah, that left one and right one image, what it indicates.
Yeah, the left one is actually the dark matter simulation they made from the image of a space. Those are stars, and they simulated some dark matter, I think. Yeah. How is dark matter distributed at that place in the space? Like with calculations and all.
Okay. And right one?
Right one is the stars there, that location. It is the location, and left one is the dark matter distributed at that location.
Okay. Yeah.
It's not a discovered it, it's just a simulation.
Okay.
Thank
you.
Yeah.
What exactly do you mean by astronomical origin? Like, aren't all particles, doesn't all particles have astronomical origin? Like, what exactly is the difference between astroparticle physics and particle physics? Is that a stupid question? I'm sorry.
No, it's not a stupid question. It's a very good question. But I think they classified as like the particles that initially found on the Earth, they're classified as a particle. And now what we are getting now from the space, they're considering them as astroparticle. Of course, all the particles originate in space and stars. I think that's the only difference they made.
Okay, makes sense. Thank you.
Can you please explain again why there was dip in the radiation observed?
Yeah, actually, I was going to ask that question here. I didn't know that. Very good question. I was going to ask this question in the end to the Sagar actually, or someone who knows cosmic rays.
So actually, I read about
Sorry,
it.
what was the question again?
Why was there a dip when increasing altitude? Why was there a dip in between, and then the ionization level increased? You can show them the graph actually, Sagar sir.
So I read about it in Wikipedia only, and it was written that initially they get ionizing radiations from the ground itself. That's why at the base they have high levels of ionizing radiations. Then it decreases, but then ionizing radiations from the cosmic ray comes in, and that's why the radiation amount of radiation increases. That's what
But
I
yeah,
thought.
why is it decreasing? I mean, why isn't there any radiation in the middle part where it is dipped? The space, the radiation that are coming from space.
No, the initial point is not because of the cosmic rays. It's like
It's because
the ground
because
activity.
Because of the ground. I understand it's because of the ground. Okay, I think I got it. Yeah. Okay. So any more doubt?
Somebody can continue, I think.
Yeah, you can.
Hello everyone, am I audible?
Yes, Samriddhi.
Yeah. I have added some animation. I mean, the points come up one by one. So I think you can just like press the
Yeah.
next. Yeah. So what are cosmic rays? These are basically particles. They're high energy protons and atomic nucleus that move through the space with the speed nearly equal to light. Cosmic ray is actually a misnomer because it's not a ray, but it's a stream of particles. Next, I think you can just complete till the points just stop coming. Yeah. So these particles they travel with speed close to the speed of light, and the composition of the cosmic ray, the particles are similar to that of interstellar materials. That is, it contains 90% hydrogen and 9% helium nuclei and other heavier nuclei, and 1% electron and positron. The positron, it's actually the uh, anti-particle of electron, not particle. Sorry. Yeah. So and it's different than the interstellar material because it has lithium, beryllium, and boron in more concentration than compared to the interstellar material. Next slide, please. Yeah, it can be divided into two types, that is primary cosmic ray and secondary cosmic ray. The primary cosmic ray is they're basically above the atmosphere. Once these cosmic ray interact with the atmosphere, they break down and they decay into different particles, that is pions and muons. So these are called as secondary cosmic rays. Yeah, and they are also called as air showers. You can also see the graph there. The what the cosmic ray ionization actually increases with the altitude, yeah, and it decreases, and then again it increases. And these muons that we detect, we can use that to estimate the composition of the cosmic ray. Also, it is important for us to know cosmic ray because they are direct samples from outer space, outer solar system, and it will help us to know more about the chemical evolution of the universe. Next slide, please. Yeah. So since we can't directly get the primary cosmic ray on the ground, there are different methods to detect it. There are two types basically, that is direct detection and indirect detection. Points, please. Yeah, direct detection is basically we should do it above the atmosphere. So we use different kinds of particle detectors in the International Space Stations, on different satellites or high altitude balloons. Now, the detectors that we use in direct detection, they're very limited. Like it is because of the size, and it's very difficult for us to use it. And in indirect detection, it can be divided into two types. That is detection of secondary particles and the detection of electromagnetic radiation by these particles. So basically, yeah, next points, please. We have different types, and in that the most easiest and the oldest type is cloud chambers. Here, as it was explained yesterday, we don't actually get to detect the particles, but we can see the path traced by these particles. Yeah, and the next we have the Air Cherenkov telescope. Here we detect the low energy cosmic rays by analyzing the Cherenkov radiation. And in this method, we can distinguish between the cosmic ray and the background radiation also. Since we are using Cherenkov radiation, it is very useful only in clear nights. And next we have the next point, please. Light from nitrogen fluorescence. So we detect the nitrogen fluorescence caused by the excitation of nitrogen in atmosphere by the showers of particles moving through the atmosphere. And in this method, we can easily find out high energy radiation, and also it is very useful in clear nights. And the next method is by detecting the electromagnetic, the radio waves caused by we sorry, we can detect the electromagnetic, that is the radio waves detected by these particles. Now the cycle of this is similar to that of particle detectors, and this has a potential to replace the Cherenkov radiation, and uh, there is a lot of scope in this in future. Next, please. Next slide, please. Yeah, here we see high altitude balloons. In the left, we can see the balloons are ready to be launched, and in the right picture, we can see the average size comparison. Next slide. Yeah, this is actually a picture of a cloud chamber. Here you can see the path of different particles, that is the low energy electrons and the alpha particles, and yeah, high energy electrons or muons. We can see those path. Next slide, please. Yeah, this is the Air Cherenkov telescope that I was talking about. Next slide, please. Next. Yeah, so what are the different sources of cosmic rays? So we have the cosmic rays coming from sun, the nebulae, supernova remnants, black hole, and active galactic nucleus, and identified source. The reason that we are not able to identify a particular source is because cosmic rays, they don't travel in a straight line. They take path of the magnetic field. Since magnetic field is not straight, it is not straight, it has curved paths all over. We are not able to identify from which source we are getting these cosmic rays. Yeah, that's my presentation. Thank you. Oh, yeah, sorry. So here we see the graph, that is the difference, I mean the number of cosmic rays that we have uh, uh, versus the energy of the cosmic rays. The pink color represents the cosmic rays that we are getting from supernova remnants, and the yellowish green color was from outer galaxy source, and sorry, that is from other galactic source, and the blue color was from extra galactic source. And the number is in a logarithmic scale. Yeah. Thank you.
Am I audible?
Yeah.
Yeah. So neutrinos are subatomic particles which are similar to electrons. According to the standard model of particle physics, neutrinos are leptons with no electrical charge. As Sagar mentioned, there are 6 types of leptons. The 3 leptons with no electrical charge are the electron neutrino, the muon neutrino, and the tau neutrino. So, and they have very little mass, and the spin is half. The Minos experiment shows that neutrinos have wave property. So this Minos experiment is confirmed that Super Kamiokande discovery that neutrinos disappear in flight, meaning that this phenomenon, this disappearance of neutrinos occurs from the wave phenomena of oscillation. This Minos experiment is very similar to the experiment conducted by Young, which shows that the double slit experiment. The wave behavior of photons in double slit experiment is very similar to the behavior of neutrons in this Minos experiment. Next slide, please. The basic properties of electron neutrino were explained by Pauli in 1930. Enrico Fermi elaborated on this principle, on this theory, and said that neutrinos are emitted in positive beta decay process along with positrons. Identification of the muon neutrino was done in 1962 on the basis of the results of the particle accelerator experiment. So high energy muon neutrinos are produced by decay of 5 mesons. In 2000, physicists at the Fermi National Accelerator Laboratory get the first experimental existence of tau neutrino. This is basically the first detection of these particles. The next slide, please. Sources of neutrinos. Almost everything we see is a source of neutrino. Fusion reactions in the sun produce neutrinos. Cosmic neutrinos are generated by cosmic rays in extragalactic sources. The exact source of these could include objects such as black holes, remnants of supernovae, gamma ray bursts, and other things. These are there are artificial neutrinos that are created in particle accelerators, nuclear reactors, and then Earth itself is a source of neutrino called geoneutrino, which helps scientists in understanding the composition of Earth. Look at how the Earth was formed and things like that. What might happen in the future and things like that. Atmosphere is also a source of neutrino. When cosmic rays crash into the atmosphere, they interact with atomic nuclei, forming mesons, which rapidly decay into muons, which further decay into electrons, antineutrino, and muon neutrino. Next slide, please. There are quite a few detection techniques. So there are scintillators, radiochemical methods, Cherenkov detectors, radio detectors, tracking colorimeters, and coherent recoil detectors. Then ice cube detector is one of the largest neutrino detectors. Is located in the South Pole. The next slide, please. So this ice cube detector is a particle detector made up of Antarctic ice. It is buried beneath the surface extending up to 2,500 meters. It was primarily built to observe neutrinos from the most violent astrophysical sources. Next slide, please. So this is basically how the ice cube detector works. So when a neutrino interacts with the Antarctic ice, it creates other particles. In this event graphic, a muon was created that traveled through the detector almost the speed of light. These patterns in the amount of light recorded by the ice cube sensors indicate the particle's direction and energy. So as you can see, these colored spheres show that sensors have detected light, and these colors indicate the time of arrival. This is the path of the particle through the detector. I'm not 100% sure of how this works, but this is the most, I think this is the basic of how this detector works. If someone can explain more about this, it would be a good thing. So one of the largest neutrino detectors there in the world.
Excuse me.
Yeah.
Yeah, my question is this experiment proves that the neutron has a speed equal to the speed of light?
I think I'll answer. So this experiment doesn't prove the speed of the particle is equal to speed of light. Rather, we know in any medium, speed of light reduces, right? By the refractive index, that property, and the speed of light reduces, right, in any medium. So if the speed of light reduces, then it could be something like 2.9 into 10 power minus 8, right? It could be 2.9 into 10 power minus 8. If in that case, if we have a neutrino which has speed 2.95 into 10 power minus 8, like if you have a neutrino which has speed 2.95 into 10 power minus 8, in that case, the speed of neutrino is more than the speed of light, right? In that medium. So that is what he was telling. Then that release some radiation called as Cherenkov radiation.
Okay.
Yeah. So you can continue.
Yeah, my last slide. So I'm done.
Right. So I'm going to talk about electromagnetic waves. So by the name itself, we understand that there's a presence of electric and magnetic fields. Now, electromagnetic waves lie on a spectrum, and this spectrum can break down into 7 categories. So you have your microwaves, your radio waves, infrared, visible, UV, which is your ultraviolet, X-rays, and gamma rays. Now, over the time period of a century, all of these were individually discovered. So you have Sir William Herschel, who discovered infrared. Then a year later, you have Johann Ritter, who discovered ultraviolet. And interestingly enough, Maxwell was the one who predicted the existence of radio waves and in general electromagnetic radiation. And then later, Heinrich Hertz was the one who proved it. Then you have Wilhelm Conrad, who discovered X-rays, and Paul Willard, who discovered the presence of gamma rays. Now, Carl Jansky, he was an radio engineer and a physicist. He discovered that there is radio waves that are originating from the center of Milky Way galaxy. And he is also coined as the father of radio astronomy. And now coming on to the next slide, we'll understand how are electromagnetic waves produced. So to put it simply, any accelerating or oscillating charge produces an EM wave. So for example, let's say there's a positive charge that's present in free space. So we know that from a positive charge, there's an electric field that spreads out radially. So now, let's say you oscillate that charge, the electric field also will oscillate. And now from an oscillating electric field, there comes an induced magnetic field. It's important to note that the electric and magnetic field are perpendicular to each other, and both of these are also perpendicular to the direction in which the wave is propagating in. Then James Clerk Maxwell was the one who coined the term electromagnetic radiation. Now, the question arises, how do we detect them? Because there are so many categories, it depends on which particular part you want to detect. So based on whichever category you're looking for, there's different kinds of telescope that will help you detect the waves that you're looking for. So if you want to detect radio waves, you have your radio telescope. If you want to detect X-rays, you have your X-ray telescope. Similarly, infrared and infrared telescope. So in the picture, we can see that there's Parkes Observatory Radio Telescope. And on the next slide, we have some observatories which detect for particular rays. So you have your Fermi and Swift for gamma rays, your New Star and Chandra for X-rays, your Galax for ultraviolet, Kepler, Hubble, and SALT for visible, Spitzer and Sophia for infrared, Greenbank and VLA for radio waves, and then finally Planck and Karma for your microwaves.
So thank you guys. So this will be our end of the presentation. I think discussion we can hold it in our Discord channel, because now we have to allow the gamma ray group to continue. So we have 5 minutes time to explain the group activity. Let me do that now. And all questions what you have, we can do it on Discord after this meeting. Okay. So please hold the questions and we can do it in Discord. So Adesh, can you share your screen?
Yeah, one second.
Sagar, I just wanted to share a thing. Actually, there's a journal called Astro-particle Physics Journal, and they publishes the research work on this topic actually. And you can publish your work there. And if anyone is interested, I don't know if it's free to read the papers or not, but you can publish your work there. It's a very good journal. Okay.
Can you send me the link?
For the journal?
Yes, sir.
Yeah, I think you can put it in the
you
journal
can
club.
Okay, I got it.
Okay. So guys, for particle physics people, that's the neutrino group. So we have a week activity, which you will be doing on 5th June. You'll be presenting you'll be presenting a PPTs based on the topic overview of neutrinos. So you can see a topic, right? On 4th June, Friday, you have a topic mentioned. That is the graded activity. So in that you have 3 topics to choose. 1, 2, and 3. We have 3 topics, and I also explained what will you be doing in that topic. Like I made a list of I made 3 lists with 16 people each. So these 3 groups will be Group A, Group B, and Group C. I'll put the list in our Discord neutrino group channel now. So in that Discord channel, you'll get the list, right? So which group you belong to, I'll be putting that. So you guys should do this thing. One is this group presentation. So everybody has to contribute for a group presentation and a group article. Okay. So you can see each group should be doing a group presentation and a group article based on that topic. So group A's topic will be the point 1. How was it theorized and discovered? And you can go in detail. And group 2's group B. The group B's topic is the second point, the basic theories of neutrino and contributions by scientists. And group C's topic is the third point, the first detection and what are the detectors, like some detector examples and current developments, all that part. So you'll be knowing the topic, and I'll be giving the group, which group you belong to, and everybody has to contribute for the slides. Okay. So PPT duration can be like not more than 30 minutes. So 30 minutes is your time for group presentation. And group article, what you can do is you can submit the group article on 5th June. Before 5th June, 11:59 p.m. you can submit the group article. So group article, all the group members can help in forming the group article, and all group members can help in forming the presentation. Who wants to present, that's left to your choice. So this is the group activity. Okay. Any doubts in group activity?
Only one people will means give the presentation, na?
No. It's left to you. Like in a group, if we have 16 people, some 8 people can give a presentation, right? Like
Means
like
it
5
will
minutes
be
each.
on the group people. Means the member will decide how to give the presentation.
Yeah, group members will discuss, have a call and interact, and then decide what to do. Okay. I'll be sending the list now itself.
And one more thing, the article will be for the each group. One article means the article will be for the whole group.
Yeah, the whole group should make an article. All members will contribute for that article, and one person can edit and give a good 1-page article with 1,000 words.
And the
Not more than
submission will
1,000
be done by only one member of that group.
No, submission, what we'll do is every member of that group will be submitting the same article. Like if group A's article is one page, all the member of that group should be submitting the same article, because only then I'll come to know you guys are active and you will be submitting. Okay.
And the article will be made by all the 16 peoples.
Yeah, all 16 people will make the article. All 16 people will make the slides and help in presentation. Presentation doing can be your choice. Who can do, who will do.
Okay. Thank you so much. Thank you.
Aren't we supposed to like prepare for the presentation on 4th and then prepare on 5th, or are we supposed to present on 4th?
No, see, what we'll do is, now I've informed right now, Tuesday I informed, you have time like Wednesday, Thursday and Friday time you have, and 5th June you will be presenting.
Okay.
Okay. So I mentioned the time to be 5:20 to 6 p.m. If you want, you can increase till 6:30, because after 6:30 you can, because we'll be having a guest lecture that day at 7 p.m. So until 6:30 you have time, 5:20 to 6:30, like one group 30 minutes.
So on 4th from 6 p.m. to 7:30 p.m. basically it's like a discussion session for us, the groups.
Yeah, you can have discussion sessions even before and after, but that day whole like 1 hour time is dedicated to discussion between you guys.
Okay, thanks.
Okay, and the quiz what it is mentioned in 5th June will not be happening. Okay, that quiz will be postponed to next week, and the quiz is not happening. Rather, only the presentation is happening. Okay.
Then we can start on 5 p.m. only, right?
Yeah, you can start the presentation on 5 p.m. and go till 6:30. Not a problem.
Okay.
Okay.
I have a doubt actually. So with this group division article and the presentation, everybody will be contributing for both of them, right?
Yep, everybody will be contributing.
Can't we choose in which group we want to be?
Because if that's happening, some more people could choose one topic, and some topic will be very less people. So then it will be like biased thing. No, we don't need any topic to be neglected. All topics are important. So we'll make the group, and this is not permanent group. It's just a random group only for this activity. This group will not be continued actually. Okay.
No, the matter is not the group. The matter is the topics. Like I am mostly interested in the theoretical topics, and many other people have different choices, different interests. So
if you have that question,
see, if you are doing the theory work, you'll have to do experiment at some point of time. Like not do the experiment, but you have to read, because theory is not everything. Of course, you can become a theoretical physicist, but you have to do experiment actually. So all things are important. You can read other articles which we will present and understand them.
Okay.
Can you share the format or sample of article in the Discord group, so we'll get the idea?
You mean the presentation what I did today? That one?
Oh no, that means article we have to submit on the 5th June. Can you explain that kind of article sample paper, so that we will get the ideas how to write the article and all those things?
Like a demo article.
Yeah, kind of.
Okay. So we don't have any sample article prepared. Rather, I can tell what you can do. One you can do is you can, based on these, if you are in group 2, your topic will be basic theory and contribution by scientists. So what you can do is you can find out for theories of neutrinos, what models they have, or you can do any one of the theory, like neutrino oscillation is one of the theory of neutrino. You can write some words about neutrino oscillation, and then you can find for contribution by scientists, right? There are many scientists who contributed for neutrinos. So you can make a list of them, or you can tell which scientist contributed for which theory and explain. You can do such stuff.
Okay.
So it's left to your idea how to present the article. Okay. So if you have any doubt, you can ask in neutrino group, and if you want after 8:30, if you still have any doubt, I'll be online. You can come to the voice channel. Okay. Now we can leave for the Maxwell equations to occur.
Hello.
Yeah.
I'm from gamma ray burst group. So do I have to like stay in the same meeting or should I?
Okay. So everybody who are in gamma ray, you can stay in the same call because the same Zoom call will be continuing for the gamma ray group. There's the electromagnetic wave group. Okay,
And
no
is
need
it
to
for
leave.
every day or like every day this will be the pattern? Like
Yeah,
on the
every
same.
day the link is the same. See, for
Okay.
any class what we do in Zoom, the same link. The link is same. Okay.
Okay. Thank you.
Okay. So neutrino group. That's all. That's all our meeting. So now we can leave for gamma ray group. So Vikrant, if you are here, and Hardik, you can continue.
Yeah, hi. Can you hear me?
Yeah.
Hello?
Yeah, you're audible.
Hardik. Fine. So how many people from Gamma Rays are here now? Vikrant, are you here?
Yeah, I'm here. Can the gamma ray people just raise your hands? And the participants from the neutrino group are welcome here. So if you want to stay back and have a discussion on Maxwell's equations, you're more than welcome. Is everyone here from the gamma ray group? Let's see. Yeah, I see. Okay.
Yeah.
Let's probably wait for, I don't know, 2-3 minutes and then see what the numbers are. Keep your hands raised if you are from the gamma ray group, so just so that we can see how many have come in. Hardik, can you keep a count while I try to share my screen and see if it works out?
Yeah, sure.
Hi, Vikrant.
Hey, yes.
Yeah.
Sorry, who's this?
Yeah. I'm Manish.
Manish,
Yeah.
yes, go ahead.
Yeah. My question is, yesterday, you have given the two questions, like if del cross f is equal to 0, then f is equal to minus of grade of some scalar function v.
Yes.
Depend. That the second one I found out, but I didn't get any means solution. Or can you tell me
All right, no
what?
problem. We'll have a short discussion on that once we officially start the session. But what is it? What's the answer? What have you got?
No, I actually searched that. I didn't get any answer regarding this. Means if del dot f is equal to 0, then what will be just like f is equal to minus of grade of some scalar function. Then
Okay, not
I
a problem.
don't know actually.
We'll just have a look at that. No issues. What about the others? Have you, were you able to find something based on this? Okay. I am
F is
audible.
F is a curl of some function, I think.
Right. Yes, exactly. So you can, the answer was already given yesterday somewhat. I'll just reiterate that. F can be written as curl of some function. I'm going to call it A, for example. So that's how you can write that. And in this case, A would be called the vector potential. I hope my screen is shared and all of you can see it. Is there anyone who cannot?
You can see.
No, it's visible.
Yeah, it's visible.
Cool. So this was about yesterday, and here you can express. So if the divergence of some vector field is equal to 0, then you can express that vector field as the curl of some other vector function, and that vector function would be called the vector potential. So here we call small f to be the scalar potential, right? So, if you're taking a curl, then it has to be a vector field. And so by default, you just call it a vector potential. Now, this comes in handy when you are trying to understand why there are no magnetic monopoles, and that's what we'll be sort of having a discussion about. We're going to directly get into Maxwell's equations. We're not going to go through the history of the derivations and so on and so forth, but I will directly write down the Maxwell's equations and then we'll try to understand their implications one by one. So I'm going to wait for another 2 minutes to see if everyone has come in. The ones who haven't raised their hands, I'm assuming you're all from the neutrino group, unless I'm mistaken. And that is okay. Yeah, that's fine. That's fine. Not a
Around 13
problem.
people have raised their hands.
13 people have raised their hands. Is it? Okay. Cool. So yeah, let's wait for 1 more minute. We'll start at 35. Oh, Divyansh, sorry, I didn't see your message. Yeah, it should be curl of some vector field. That's correct. Okay, so I will be unable to see the chat box for quite a while. So if you have any questions, do put them in the chat box, or you are free to interrupt me in between to ask your questions. All right. So let me open a new page and write down what we're going to be doing today. Now, most of you would already be aware that electrodynamics is a vast field in itself, and a few people at the advanced level would realize that this is what we call a classical field theory, right? So I'm just going to write it vaguely. It's a classical and then a field theory. All right. Hardik, do let me know if my internet or something gets glitchy and you miss out on something, and this applies for the rest of them. If you feel like you've missed something, please do let me know if my glitchy or something. Okay. All right, so let's 36. It's a good time to start. Okay, so we'll just write down the Maxwell's equations, but we'll write them in two eras, two different ages. Right. So the first age we're going to write is before Maxwell. All right. Like, now you might just tell that how can you write Maxwell's equations before Maxwell? But they're just equations of electrodynamics initially, right? They're just equation of ED. I'm just going to write that as ED. Now, what were these equations? Let's have a look. The first one is tells about the divergence of the electric field, and that is equal to rho over epsilon naught. Don't worry about these fancy mathematical things. We will focus more on what they mean. All right, I'm going to tell you what the rho is, what divergence means here, what the epsilon naught is, and so on and so forth. All right, the second equation tells us that del dot B, the divergence of the magnetic field, is 0. The third tells about the curl of the electric field, and that is equal to minus d dou B over dou T. And the fourth is that the curl of magnetic field is equal to mu naught times J. All right. These are the equations of electrodynamics before Maxwell's time. And now let's look at what are these called. They all have names except for the second one, unfortunately. The first one is called Gauss's law. Some of you might be familiar with it, some of you might not. That's totally okay. The second one, unfortunately, has no specific name, and there's no name to call it. The third one is called Faraday's law. Michael Faraday. I'm sure most of you have heard about his life story. And the last one is called Ampere's law. Ampere from the unit of current. Faraday is the unit of magnetic field, I think. No, about inductance. I'm not sure. I think inductance, right? So we'll see where exactly do all of these pop out from. Okay.
No, it's for capacitance, I think.
Yeah, capacitance and inductance as well. In fact, Faraday's law comes from mutual and self-inductance. So we'll go a little bit into the history of that. Thank you very much. Okay. The negative sign here in the third equation is purely conventional. We'll see why that negative sign comes in. It has to do with Faraday, how he discovered the electric and the magnetic fields and so on. Okay. Now, we'll understand what is wrong with this. Why did I decide to call these equations before Maxwell? All right. Now, this has to do with a little bit of vector calculus, but you don't have to worry about it too much. Okay. The problem lies with the fourth equation here. These set of equations are supposed to obey every system, but it was found that the fourth equation does not, behave the way it should behave. And I'm not going to get into the details of that. But what happens is if you apply the divergence to this thing, if I was to take the divergence of del cross B, it should vanish, right? Because something that is curling, right, something that is going in circles cannot spread out. That's not possible. So it should be equal to 0. But then I don't get that, right? If you just follow the simple rules of differentiation in 3 dimensions, what you actually get instead of a 0 is you get mu naught times del dot J. Now, to understand why exactly is this not equal to 0, we have to get into every single term that is present here. And so we start our journey with the very first Gauss's law, which in its differential form says that the divergence of V is equal to rho over epsilon naught. Now, I'm not going to get into the derivation and everything of all of these equations, but I will just roughly tell you what they mean. All right. So we'll assume, let's say, a random region of space. We're going to be working in 3 dimensions always from now on, because we have all these 3-dimensional vector operations. The del operator is a 3D vector operator. So we're going to be in 3 dimensions right now. Okay, so now we'll consider some region. And let's say we have a single charge Q. Right? And I want you to pay attention to the single charge Q here. Okay, because that's what's going to help us understand about the second equation over here. All right. Now we see here that if there is a charge Q, then it is going to sort of create an electric field which can be experienced by another charge. So the electric field is going to be spread out like this. And the way you detect this electric field is by the Coulomb's law, which I'm sure all of you are aware of. And if you're not, please do let me know. I'll just give you a brief just about that as well. It's not a big deal. Okay. So this is the electric field that is given out by this charge, that is with the charge as its origin. All right. Now, if you consider a small volume element here, let's say a small volume element with volume, let's say dV, and we know that dV is just the product of its sides, dx, dy, dz. It's the volume of a cube, basically, or a cuboid, for example. Right? It's just that. Now, what this law tells me is the divergence implies that the spread, right? So I'm going to write this a little bigger here. We have the divergence of V is equal to 1 over epsilon naught times rho. So I'm going to switch the color to blue. And the left-hand side just tells me about the spread of the E lines, the electric field lines. These white lines that I've drawn, it just tells me about the spread of that. All right. And the right-hand side, 1 over the epsilon naught is a constant, which we'll come to later. The rho here stands for the charge density. All right. And what exactly do we mean by charge density is the amount of charge that is present in a unit volume. So if I was to take the small volume dV, the rho would tell me about how much charge is there in that. All right. So in other terms, the total charge in the region is equal to rho, the density, times the volume. All right. That gives you the total charge. And that's all Gauss's law is all about, right? Why exactly does this tell me about the spread and the charge density? You can always apply the divergence theorem, which I won't be getting into. The other way to look at this is if you convert this into integrals. And in a very simple way, I can write the integral as, and yeah, I'll keep this in blue itself, since it's not that important. It's just that E dot n cap over some area is equal to Q over epsilon naught. This sort of tells me roughly about the flux of E lines. as to how much, how many electric field lines are passing through this small volume or some area element in this region, and that's all Gauss's law is all about. All right, and now we can move on to the next thing. So since we are at electric field, we can extend this idea to the curl of electric field. We can try to find out how much does it curl. We can see. So can anyone unmute and immediately tell me what should the curl of electric field be? If my
0.
white lines are exactly, yes. Who was the? Can I know your name, please?
Naxxatra.
Nice job, nice job. So what you would directly conclude is that the curl of E is 0, because you clearly it doesn't curl, it doesn't rotate, it doesn't go in circles, it just spreads out, right? So it makes sense. But then comes along Faraday. I mean, this is what you thought should be. Then comes along Faraday. So we're going to look at the third equation now. It's a little jump, but it's okay. Right? We're going to look at Faraday, who said that the curl of E is not equal to 0, but the curl of E is equal to minus the change in the magnetic field with respect to time. Now, this is a very bizarre, non-intuitive thing that you might think of at the very first, at the very first look of it. But it's a fairly simple experiment that you can do if you have a few wires at your home and a small battery. If you're an electronics student or something, you might, do this, or you can just have a thought experiment. Right now, let's say I just have like a magnetic field here. Okay, this is a magnetic field. I'm going to represent it with P, and I have some current loop. Right, the current is flowing through it. There's nothing serious happening. The current is flowing through it. Now, what happens is if I move this current loop back and forth, there's a change in the current that is flowing. All right. So if let me make this simpler for you. Let me make this very simpler. We have, let's say, a magnetic field, okay, and you have a small LED bulb. Okay. If you just keep it, it's not going to glow. But if I was to move this LED bulb front and back, it is going to give out light. And if I stop moving it, it's not going to give out light. So with this, Faraday sort of deduced that if what is happening is this magnetic field has some magnetic field lines. Let's just draw it like this for now. We'll not worry about why I'm drawing it in curls, right, why I'm drawing it in circular manners. All right. What Faraday deduced that because of this movement, there is a change in flux. Change in flux of P. And what flux essentially means is the number of field lines that are passing through a given unit area. All right. And through this LED, for example. All right. Faraday deduced that there is a change in flux that is happening, which gives rise to some sort of EMF, electromotive force. You might have heard this in your 12th grade, electromotive force. In other terms, you might have seen this expression, epsilon equals minus P phi over dt. Now, I'm not exactly sure if Faraday did put this down in a mathematical form because he didn't know math. But this is what he deduced, right? That's why we call it Faraday's law. He drew several diagrams that you can access on the Royal Society website. But this is essentially what Faraday's law is all about. And what this tells is that a change in flux induces some sort of EMF or some sort of potential. And that is the reason why the LED is glowing, right? And if the LED is glowing, that means there must be some charge that is flowing through, which means that there is an electric field that pops into existence. So an indirect deduction of this is that a changing magnetic field induces an electric field. Yeah, sorry, go ahead.
Can we say that the Faraday's law is only applicable when charge moves?
Exactly, yes, that's absolutely correct. So if the charge was stationary, then there would be no change in flux, right? the number of field lines flowing through it would be the same in every unit of time, at every second or every hour. It's going to be the same if you're not moving the charge. Right. So here, moving the LED implies you're moving the charge. I gave the LED as an example, but if I was to replace this LED with, let's say, some current loop, right, some wire, for example, okay, attached to some bulb, right? Just a simple arrangement. There's nothing too complicated about it. This is just a bulb, and I've attached it to a wire, and part of that wire is inside the magnetic field. Now, if I was to move this wire back and forth, the electrons inside this wire that constitute the electric current would start moving because there is a change in flux. And therefore, there is an EMF produced, a potential that is produced, and hence the bulb would glow as long as you keep it moving. That's essentially what Faraday's law is all about. And with a little bit of calculus here and there, Maxwell deduced that, I'm not sure if it was Maxwell, but you can deduce that the curl of the electric field is not zero, but is actually equal to the change in the magnetic field. It's a huge jump from the EMF to this, but it's just simple vector calculus that you can do. I'll just write it on the side for those who are interested. The EMF can be written as the line integral of E dot dl. You don't have to worry about this part. I'm just doing it for the people who already have an idea of it. Okay? And this is equal to minus d phi over dt. If you just say that E is related to B, then and then you can just you can just write this as E dot dl equals minus of dou B over dou T dot dA, and then you can just get rid of the integrals by applying Stokes' theorem, and that gives you curl E equals minus dB over dt. What this tells me is that a change in magnetic field induces an electric field. Yeah, I can see that. But the converse also is true. If there is a change in electric field, then you have a magnetic field that is produced, and you can see that in this part here of the board. Right. So if there is some change in E, then to keep the equality, phi must change, and that's like a very crude way to look at it. Okay. Now, any questions so far? Something that I can keep short so that we don't stray away.
I think that equation was given by Lenz's law in 12th.
Yeah, the negative sign is because of the Lenz law, which so the negative sign is because I'll put this in a very fancy statement, the way Griffiths puts it. The negative sign is because nature, I think the word he exactly uses is abhors a change in flux. That's your Lenz's law, basically. Right? Nature always opposes whatever it is that is causing a change in flux, and therefore the negative sign sort of tells you that it's in the opposite direction, whatever it is. So if I was to move this in the left side, my potential would be forming to the right side, roughly, something like that. Right? It would be opposing the motion, and that's why you have a negative sign coming in.
Hello.
Yes.
Yeah, I was saying that this electric field is not always the like generated due to, it is not always the induced electric field. If the like if we say that magnetic field is varying and then electric field is producing, then it is not induced. Like only when the electric field is varying, we say a varying magnetic field is produced, and at that time that electric field is not induced. It will be just a electric field, static electric field, right?
I'm not quite sure I get your question at the moment, but I will get back to you on that. If that's okay.
Yeah.
We can have a discussion on Discord later on this.
Sure.
I don't recall it at the moment because I do remember studying about it, but yeah, I'll get back to you later on that.
Yeah, no problem.
Thank you. Okay. So one additional piece of information that we need is the continuity equation. And if you've studied a little bit of fluid stuff, then what it simply says is the amount of the stuff that goes in must come out equally. It's just that, right? Whatever goes in must come out, and the flux must be, the net flux rate must be constant. In a mathematical form, you just put this as del dot J equals, or let me just put it like this, plus d rho over dt equal to 0. All right. Now, you don't have to worry about what J and all here is, but I'll just tell you what they are. J is called the current density, okay, which basically means it is the current per unit area. You can write this mathematically as di over dA. All right. So it just tells you about the flow of current in a region. All right. Now, rho we've already encountered is the we'll just call it density here. Let's not be very specific. And density, it's you already know what density is, so you don't have to really worry.
I think it is a charge density, I think.
Yes, but the same kind of equation also holds for fluid mechanics. So the current here can also refer to liquid current, fluid current. So I'm not, actually, since I've already defined current density, so I can already say that this is charge density. Makes sense. Thanks. Yeah, density of charge. So that just tells you about charge per unit volume. Okay. Don't worry about the dimensions and stuff. It's not really it's not of huge importance right here. If I can rearrange this equation, del dot J is equal to minus d rho over dt. Now this you can sort of make sense, right? How you can make sense is that the negative sign implies the outward flow decreases if you take do rho over do t, right? That's the rate of flow. It decreases the charge, or in other terms, the charge in the unit volume. Right. So what this is telling you basically is that if I have a region, I'm just going to draw a square with some, let's say, with some charge density rho. If this keeps flowing out, then eventually this rho is going to decrease. That's all there is to it. Right. If it's like if you have a bucket of water and you poke a hole in it, the water keeps flowing out and the bucket is eventually going to get empty. That's all. That's all continuity equation is saying. And if I was to measure how much is going out and how much is there in the bucket, the net amount is the same quantity. So if I had like 10 liters of water and I measure how much is flowing out and how much is left in the bucket, it's going to be 10 liters all in all, ideally. Right? That's roughly what this is all about.
Excuse me.
Now,
when this del dot J becomes 0, means at what condition?
Very good question. Are you familiar with differential calculus?
Yeah.
Okay. So del dot J is equal to 0 if and only if rho is a constant.
Yeah, right.
Obviously, right? If you can't differentiate a constant, so and what it means that you have a constant density throughout time. The density doesn't change with time.
Okay. Means it must be constant.
Yeah, exactly. Constant with respect to time. That's more being specific because it's a partial derivative only with respect to time.
Oh, okay. Can you give me example? Means the real life example where rho will be constant, because in generally we say the charge is going outwards, means it is on the surface, it is moving. So at which case it is a constant? Can you give me some example?
I am not aware as of now of any these kind of systems where rho remains a constant, because like the last statement that I've written, if it is, charges, the electric field would flow out, and so eventually the density is going to fall down, right? So I'm not aware of any scenarios where rho remains a constant with respect to time, but I will look it up, and if I get something, I'll make sure I'll let you know about it.
Okay. Yeah. Thanks.
Yeah. Mathematically, though, that's when the continuity is when del dot j is 0. It implies it does not diverge, it does not spread out, right? So it's like it doesn't even flow out in a sense, right? So if this is the case, then it doesn't even flow out. It's just there. There is no spread as well. It's just a very static thing. It's
Or
just
we
there.
can say that
It's
it
not
is a
moving out.
static Coulombic system. Can we say?
Yeah, that would be a good way to put it. But as I said, I'm not aware of any physical systems that actually do this. So yeah, ideally you can build a system like this. You can just say that the rho is constant with respect to time, but in real life, I'm not sure.
Okay. Yeah. I think there must be a conducting and non-conducting scenarios where charge is distributing along the surfaces. I think
Yeah,
that will be
I might
connected.
have to look up on that, and I can let you know. In fact, you
Yeah,
also can
if
look it up.
I think
Yeah.
non-conducting spherical, if we remember from the 12th standard, a non-conducting spherical body is the charge in that does not distribute, so it can act as a constant charge density body.
Yeah, but there you take the density not as a function of time, right? So
I mean,
you don't even have to consider time dependence there.
yeah, it will not change with any variable, not only time.
Yeah, so yeah, that could be an example, but before I tell you a definitive answer, I don't want to give you a wrong answer. So I'd rather look it up and make sure that what we have here is correct, if you don't mind. Yeah. I hope I don't know if that was satisfactory enough. I'm really sorry about that. Okay. Sorry, was there a question? Another question?
No, it's okay. You can move ahead. Thanks.
Yeah, thank you. Okay, so now we'll come back to the second question, second equation, which said the nameless equation, which said that the divergence of B is equal to 0. Now comes back our question that I gave you yesterday, that if divergence of F is 0, that implies that you can write F as the curl of some other function. I'll call it B here. Okay. By the same principles, we can write B to be equal to del cross A. Okay, and this is one of the most important, I wouldn't say result, but an implication of what we have. And this is sort of the definition of what we call a vector potential in magnetostatics. Now, why is this important and everything is involves a little bit of higher level math. So I won't be getting into that, but you're free to go ahead and understand why exactly vector potential is important and how it helps with the Maxwell's equations and so on. But what I will tell you about is what these two equations together imply, right? And this is where Dirac became really famous. Dirac? Yeah, that was Dirac. Okay, so let's try to understand what's happening here. So we have del dot P equal to 0, and we have B equals del cross A, right? So if I was to put that back here, del cross A equal to 0, obviously anything that curls is not going to spread out, and so this makes sense. So that's just like a verification if what we've written here makes sense. Okay. Now what del dot B0 tells me is that B doesn't spread. Okay. And what B equals del cross A tells me is that B forms closed loops, and loops takes care of the curl fact, right? Loops are circular, so there is obviously going to be some sort of curl. We'll compare this scenario with the electric fields. Okay. So if we compare the left-hand side equation, For electric field, we had del dot E equals rho over epsilon naught. And what it basically means is that it's not equal to 0. Right? And what that tells me is the electric field, if I have, let's say, a point charge Q, the electric field does spread out in all directions. Right? That's what it tells me. But the fact that B doesn't spread implies straight that you cannot have a Q for B. Right? Might be too much of a jump, but what this implies is that there exists no magnetic charge. And how do I deduce this? Is because if I had a magnetic charge, then the so-called magnetic field, like the electric field, would spread out, and which means the divergence of B would not be equal to 0. It would have had some other quantity like rho over epsilon naught or something like that. But it doesn't. So there is no magnetic charge. And when you do a little bit of electrostatics and magnetostatics, this implies further that there exists no magnetic monopole. Which means if you have a magnet with a north and south, if you split them, you're still going to get a north and south. You can't isolate north completely, and you can't isolate south completely. All right. And this entire thing sort of manifests itself in the fact that any magnetic system, I'm just going to take a small magnet here with a north and a south, it doesn't really matter, is always going to have field lines like this, which are closed. You can say they originate from the north and go close in the south, right? Yeah, so this sort of manifests itself in that. The fact that B forms closed loops implies there are no magnetic monopoles. And since there are no magnetic monopoles, the field lines are always going to be curved. Sorry, there was a question. Was there a question? I'm sorry. All right, I'm going to assume everything's fine. So
I think this equation become invalid if we consider the quantization of electric charges.
No, it doesn't, because magnetic fields arise when your charges are in a steady state of motion. All right, whereas electric fields deal with stationary charges. Right, so even if you do charge is already quantized. So even if I was to put this Q as 1, right? I'll take a small eraser here. Even if I was to put this Q as 1 here, it would still hold. The divergence of B would still be equal to 0, right? But that gives me a very fun assignment or a very fun question for all of you to ponder upon, is if del dot B was not equal to 0, what would it look like? Right? If del dot B was not equal to 0, how would it look like? Like, would it look like Gauss's law? Would you have any other Faraday's law kind of a thing? That's something that I leave for you to explore upon, right? Because that's a very fun topic to look at. And that sort of also justifies why you can't have magnetic monopoles until you introduce the quantum field theories and you prove that you need magnetic monopoles for quantization of charge, right? It's like implications that take place, but for our cases right now, since we're not getting into quantum field theory, we will go on with the fact that magnetic monopoles cannot exist. All right, and if they did exist, right, that means that the divergence would not be equal to 0 because there would be some sort of spread. I want you to look up on how this spread would look like. I mean, how this equation would look like. So basically, I just want you to find out if you can write del dot B equal to something. I'll put a blank, assuming it is possible. It's a very simple thing if you just look at it for the first time, but yeah, there is reasoning behind why exactly would that form make sense and why not anything else. Right, so this is like a fun thing that I'm leaving you with. And with this, I'll move on to the final Maxwell's equation, or Maxwell's equation before Maxwell, which is the fourth
I
one.
have a question.
Yes.
So what exactly would be magnetic monopole? Can you please define it?
Okay, so which is why I said you would have to do a little bit of electrostatics and magnetostatics, but I'll try to cover it as simple as I can. Let's look at electric dipoles. Right? This is something that you would have done in your 12th grade as well when you try to find. So it's defined as P equals Q times the distance between them. Right? This is something you would already be familiar with, and this expression might be familiar already. Now, what this tells me, is we have a system of two charges. One is plus Q and the other is minus Q. Now you can define D to be in any direction, but it's just the distance between these two. All right. Now we call this dipole because you have two poles here. This is one pole and this is the other pole. The plus and the minus together make a dipole. In electrostatics, okay, where the charge isn't moving, that's why it's static. Right? Electrostatics is the study of stationary charges, the charges that are not moving. You can have just a single charge plus Q just lying around there, and it is going to give out these field lines that go away from it, however you want to represent it. Right? And if you had a minus Q, then the field lines would be coming towards it. That's how you define your plus charge, your plus and minus for your batteries and so on, right? What happens when you switch to magnetostatics? In magnetostatics, the charges are in uniform motion. Now, from our classes in Newtonian mechanics, regular classical mechanics, uniform motion just implies that they don't accelerate. All right. What happens is when you study magnetostatics in a little bit of depth, you will realize that you can only have pairs of, I'm going to write them as north and south here. Okay? You can only have these pairs. You cannot have north here and you cannot have south here. They are still going to be related. All right. And if I was to break this here, then a new south and a new north is formed here, and then these two pair up. Right? So by a monopole, what I mean here is you cannot have just an N and just an S. That's what a monopole implies. Right? So here plus Q is a monopole, minus Q is a monopole. So these are here your monopoles. They can exist independently. But here in magnetostatics, they cannot exist independently. They have to be in pairs of north and south. That's what I mean by a monopole. Does that answer your question, whoever asked?
Yes, but I wanted to ask one more question.
Okay.
If an electron is moving in uniform motion, will it be a magnetic monopole, dipole? Will it be magnet? Will we consider it in magnetostatics or not?
Okay, if the electron is moving in a steady, in a uniform motion, then you consider magnetostatics. All right, but then the whole point of having electrodynamics here, in the end, when you get into the bigger picture, it just shows you that these so-called electric and magnetic fields are just things of your perspective. All right. When you get into the relativistic part of electrodynamics, you will learn that the so-called magnetic field doesn't actually exist for the electron itself. Right? It's just something that we observe. It's something that we give to explain why an electron deflects the way it does if you put a magnetic field in it. If you put it in a magnetic field. All right. So yeah, so far what appears to be very different topics in the end turn out to be two sides of the same coin, which are connected together by relativity. That's all there is to it. Does that answer your second question? I'm not sure.
Yes.
If you're still not satisfied, we can have a discussion on Discord later on. Right? But we do
Yeah,
have a
all right.
time constraint here, so I am forced to move forward.
Yeah.
Right.
And
So we'll come to the
there
last.
have been some
Yes, go ahead.
researches where they have proved magnetic monopoles in some
Sorry, I
materials.
didn't get that. Can you repeat yourself?
There have been many no, not many, one or two discoveries, I think, where they have seen a material having magnetic monopole.
Yes, but that I have read a little about those, and what's happening there is they're apparent monopoles. All right, what they've done is this: they keep flipping those magnets around, those atomic magnetic dipoles around. They just keep flipping it so much that you feel that you have a separated north pole and a south pole, but in reality, if you look at the entire thing as a whole, you don't. Right? So yeah, that's how it looks like, but I mean, that's the closest we've gotten to getting a monopole so far.
Okay, means it is related to relativity principle, special relativity.
So,
Means it is apparent thing we are observing.
yeah, can I get back to that after I finished showing you the fourth equation? That's a fun discussion, but can we just postpone it a little bit until I finish this? I'll be sure to get back to you, right?
Yeah, no problem. Yeah.
Okay, thank you very much. We'll just finish this off, and we'll come back to why electric and magnetic fields sort of are two sides of the same coin. Okay, so now we've been talking about Maxwell's equations. If I go back all the way, we've been talking about these equations before Maxwell, and now we come back to this fourth equation, del cross B, the curl of the magnetic field, equal to mu naught times A. Mu naught again is just a constant that comes in with magnetic fields, so you don't have to worry about it. Okay. Now we look at this. All right. So we have before Maxwell, del cross B equals mu naught G. Now, like I said, the problem lies when you try to apply a divergence to it. Right? The problem lies here. If I was to apply a divergence on the left-hand side, this should give me a 0, but it doesn't. What it gives me is mu naught times this quantity, which is clearly not equal to 0. It need not be 0, right? Like from our continuity equation, we only saw when it was equal to 0 is when when the current is steady, when it doesn't change with time, right? That's only that is the case where this divergence is equal to 0, and then it is satisfied. But in general, it need not be. It's not necessary for it. So here's where Maxwell jumps in, right? Here's where Maxwell jumps in, and he's like, oh no, this is not the right way to interpret this entire thing. But what we do is we will apply the continuity equation. What we'll do is we have the continuity equation as follows, right? And he said, we also have Gauss's law, which is the first equation. We have the Gauss's law as del dot E equals rho over epsilon naught. And Maxwell sort of, I'm not going to get into the details of this, but what he did in very crude terms is he wrote rho equals epsilon naught times the divergence of this. And since epsilon naught is just any other constant, I'm happy to take it inside. And I can write it as this. Okay, and then you just put it back here. So your continuity equation becomes minus dou by dou t of rho, which is del dot epsilon naught E. Okay, and they're all independent. Your del is an operator that depends on x, y, and z, and it's not dependent on time. So I am justified in doing this. Okay, dot epsilon naught dou E over dou t. Now you just put this back up top here, and what you actually up top here, right? And what you eventually get with after a little bit of simplification is del cross B equals mu naught J plus mu naught epsilon naught dou E over dou T. This is called the Maxwell's correction. Okay, Maxwell correction to Ampere's law. Okay. Now, of course, Maxwell had other reasons to do this, but the reason he did this in the end, in the bigger picture, is because he said from Faraday's law, we know that a magnetic field, changing magnetic field induces an electric field. But then what about the opposite? Would that work out? And all in all, in the big picture, this is how he sort of told that yes, it does. I mean, what this tells you is that a changing electric field, which is dou E over dou T, induces a magnetic field. So this should answer the question that one of you had told about, which I said I'll get back to. Yeah, so a changing electric field induces a magnetic field. This is called the Ampere-Maxwell law, crudely, vaguely, but yeah. So if the electric field was constant, for example, then we get back our original term, which is called the Ampere's law. Okay, so if that dou E over dou T was 0, we get back our original Ampere's law. So there's no fault here. We get back our mu naught times J, and everything's good so far. But this is a more generalized case right here.
Okay,
So
means
now we are in a
if
state.
can I ask a question?
Yeah, go ahead.
Yeah, if a charge in the uniform motion, then also we can say that dou E by dou T is equal to 0, right? If charge is moving in a uniform motion.
If charge is moving in a uniform motion, then it has what is called a steady current. And if you have a steady current, then I do believe that a magnetic field is formed, because magnetic fields are formed only when the charge is in motion. So yeah, what you have is not appropriate. I mean, what you just said.
Okay, means dou E by dou T
is still going to exist.
Okay. Okay.
Right? Because so when you look at it that way, what Gauss's, so I see where you're coming from, if I'm correct. Your reason for saying that is because of Gauss's law, right? It just tells you about the divergence of the electric field is from electrostatics. When the electric field is constant with respect to time, the charge isn't moving anywhere; it's just at rest, right?
Yes.
But
yes.
here we are looking at the time dependence of the electric field. Whereas this equation here, the boxed equation on top, the Gauss's law, tells you only about the space dependence. The del operator there only tells you about the space dependence. It just tells you about the three-dimensional behavior of the electric field. It doesn't tell you anything about the time.
Yeah.
Does
got
that
it.
answer your question?
Yes. Yes.
Yeah.
Thanks.
So Maxwell, this entire correction was done by Maxwell, and he called this quantity here, the quantity that I'm circling in blue, he called it, it's a mess, he called it the displacement current. Yeah. So now we are in a state of writing our Maxwell's equations in their final beautiful form. And I'm going to put them in yellow because I believe yellow looks good on a black background. So we have the first equation, which is the Gauss's law, which tells me about the divergence of the electric field. The second, we'll call it nameless. And this tells me about the divergence of the magnetic field, which is 0. The third is called Faraday's law. And this tells me about the curl of electric field. And the last one We'll call it the Ampere Maxwell law. This tells me about the curl in the magnetic field, which is mu naught times J plus mu naught epsilon naught dou E over dou T. And if you think this slide looks pretty, you can take a screenshot and make it your wallpaper. It's your wish. So I hope I have been able to convince you about what these 4 Maxwell's equations imply and what importance they hold. But one most important or famous consequence of these is about the speed of light, right? You would have heard in pop science talks that solving these Maxwell's equations give us the speed of light. Well, let me tell you, you don't have to solve it. Okay, you don't have to fully solve it. You just have to compare it with something that some of you might not know about. So I'll just quickly show you what that is. Okay, so we're going to consider the last 2 equations. All right, so I'm going to write them again for our convenience. We have del cross E equals minus dou P over dou T. And we have the 4th equation, which is del cross B equals mu naught J plus mu naught epsilon naught dou E over dou T. Now, this is the only proper derivation that I'm doing. Okay, what we'll do is we'll apply curl. We'll take the curl of all these expressions. So what we'll do is del cross E is equal to del cross. I'll get back to that. Right, we just applied curl on both sides. Now there is a vector calculus identity, which I'll just give it to you as it is. It just says that the curl of E is just equal to the gradient of the divergence minus the Laplacian. Now you don't have to worry if it looks too fancy. No worries at all. Okay, and that is equal to minus dou by dou T of curl of P. Okay. Now, if we say, let's say we're in vacuum. Okay. In vacuum, there are no charges. Right? We say that the vacuum is neutral, so there are no charges, which implies that rho is 0. All right, and is anything else 0? J, the current density, is going to be equal to 0. Okay. So using that fact,
I think we get a equation here.
Sorry, yeah.
I think we get a wave equation here.
Exactly. That's what I'm getting at, right?
Yeah.
That's a very good guess. So if in vacuum, if you have no charges, then your Gauss's law just becomes 0. And if you put that back, and from if you put this del cross B expression up here, this is equal to 0 since J is equal to 0. What you get is del cross Laplacian of E is equal to minus. You get minus? No, you don't get minus. Sorry. You get mu naught epsilon naught dou squared E over dou T squared, the second time derivative of the electric field. Okay. Now, if you were to apply the same curl operation here, I'll just quickly write it without speaking it out. I'll write the final wave equation that you get out of this. Okay, so now you realize that these so-called electric and magnetic fields in the top equations, in equations 3 and 4, they were coupled, right? We had E in terms of B, and then we had B in terms of E. But now what we've done is we've decoupled them. We've sort of removed the E and B dependence in equations 3 and 4. We've sort of separated them, all right? But then what you realize that if you are to separate them, they satisfy something, right? These equations satisfy the 3D wave equation. All right, and why do I say they satisfy the wave equation is because the wave equation is of the form del squared F is equal to 1 over V squared dou square F over dou T squared. Right. So let me switch all of this to a new page. If you're writing down notes, it's totally fine. Even if you miss out, I'm gonna just put this on the next page. All right. So we have equal to mu naught epsilon naught dou E over dou squared. And then we have dou squared B equal to mu naught epsilon naught dou squared B over dou T squared. The general wave equation is del squared F equals 1 over V squared dou square F over dou T squared. Okay. Now, just by mere comparison, if you compare these blue circle terms that I'm circling, this, and this, right? You directly get what you need, which is 1 over V squared is equal to mu naught epsilon naught, right? Coincidentally, when you calculate this quantity, you get 299,792. Actually, no, not this quantity. But if you were to calculate V, right, you get 299,792,458 meters per second. And coincidentally, this was equal to C, the speed of light. And therefore, you can conclude, light is electromagnetic. Why do I call it electro and magnetic? Is because it satisfies both the equations. It satisfies the equation for E, it satisfies the equation for B. And therefore, light is electromagnetic with a velocity C equals 1 over square root of mu naught epsilon naught. And there you have it. This is sort of like the proof of why do you call light to be an electromagnetic wave. And with this, I conclude today's session. And it's exactly 8:30, so I'm glad I didn't take any extra time. So thank you. That's the end of today's session. And it's open for questions now. I'll try to answer as many as I can.
Yeah, Vikram, I have one question. If divergence of some function is 0, then it represents some vector function, right? Vector potential, correct?
Yes.
So if means that there is something is rotating. Okay, so if something is rotating, that it has some kinetic energy. So this potential, what kind of potential? What it represents?
Okay, that's an in-depth discussion about vector potential. Can we have this on Discord rather, because it will take quite a lot of time to understand what it exactly means, because for that we'll have to get into how magnetic fields behave in matter, right? When you apply a magnetic field to some substance, you try to understand with this vector potential what exactly is happening, how the magnetic dipoles are formed, and they are what gives sense to what this vector potential is all about.
Okay, no problem. Yeah, we will discuss on Discord. Yeah.
Can you provide me a material regarding the transformation of the vector potential with the using of Heisenberg pictures?
With the using of, sorry, I didn't get the last part.
Heisenberg picture.
Heisenberg pictures. I'm not sure if I haven't heard of any Heisenberg. Are you referring to the quantum mechanical?
Yes.
Okay. I'm not. I don't have any resources at the moment ready, but I can search for a few and I can let you know.
Okay.
Yeah.
I have a question.
Yeah, go ahead.
Yeah, I wanted to ask if a material is electromagnetic or behaving electromagnetic, will the equations that you mentioned, will that be able to prove that material is electromagnetic? Not.
Wait. If I understand your question correctly, you're asking if a material is electromagnetic. Is that your question?
Yes. How will we know whether a material is electromagnetic or
Okay. So one thing, when you start dealing with materials, okay, these equations don't hold. You have to modify these equations again. Okay. What happens there is you have extra stuff that is happening. So in the case of electric fields, you have, when you apply an electric field to any material, there are additional electric fields that are formed inside because of the atoms that are there within that material, apart from the electric field that you are applying. All right, so that gives rise to extra currents in the volume and on the surface. So you'll have to account for that. And similarly for the magnetic field, right? When you apply magnetic field to some matter, their behavior changes. There are magnetic dipoles formed, and a neutral atom sort of gets disturbed to form small mini magnetic dipoles, right? The entire what do you call it? The equilibrium is disturbed. So once you are dealing with that, then you look at the passage of electromagnetic waves and see if they can pass through it, and you see how they deflect off, if they do deflect, and so on. So you sort of, in the end, in the bigger picture, you modify your wave equation itself. The wave equation in material media is going to be different than what I have derived so far. And that would give you your answer.
Okay. So if there is, so you are saying that if we apply an external electric field, then there will be internal electric fields that will be created.
Yes,
right?
That's roughly what I'm trying to tell you. So there are extra potentials that are formed inside, right? So there are extra electric fields that are formed because of these small polarizations occur. If you're aware of polarizations, then polarization occurs when you apply an electric or a magnetic field. There are magnetic polarizations that occur or electric polarizations that occur, which results in the formation of dipoles.
Okay. So if a light interacts with a material, it is because of these things or just?
At the microscopic level, you have to, just give me a moment. It's something that's come up. Yeah, so when you're studying the interaction of light or the electromagnetic radiation with matter or inside matter, then that's the whole area of optics, right? You try to understand how the index of refraction works, the refractive index, and then you also introduce a quantity called the Poynting vector, which tells you about how much of it actually passes through the media. It tells you about how much can it penetrate. It's called the skin depth if you want to look it up, right? So you calculate all of those and you make up scenarios where you have normal incidence of the electromagnetic radiation, where you have maybe oblique incidence, at some random angle greater than 90 degrees. But all in all you have to do is study about how the electric and the magnetic fields are dependent on each other. There's a chapter on Griffiths if you want to look up. I think it's chapter, let me check up. There's a whole chapter on electromagnetic waves, and there's a section dedicated to electromagnetic waves in matter. And that's where you introduce these quantities called the Poynting vector and so on, which tell you about how much an electromagnetic wave can get in the material, right? And the beauty of this study of electromagnetic waves that you do is that just by studying a few special cases, you get your laws of optics right there without even worrying about the electric and the magnetic fields. You get your Snell's law, and then you get your angle of incidence equal to angle of reflection, and so on and so forth, right? So I would recommend you just go through that section on electromagnetic waves in matter. And that will sort of help you get an idea as to how light interacts with matter at that level, at the level of magnetic and electric fields.
Yeah, I have one question. Is the skin depth is depend on the material medium? Means skin depth is upon one upon E times something the penetration happens. So it is depends on the material. Means the medium properties
It's
or
sort indirectly, yes, it does, because the way you define skin depth again depends on the relative permittivity and the permeability of the medium you have. Right, so these mu naught and epsilon naught get replaced with just mu and epsilon. So let me just tell you about how the equations of these Maxwell's equation look in matter roughly. Okay, in one of the specific cases, in conductors, I'm going to show you how they look in conductors specifically. Okay, so in conductors, I hope my screen is still shared. Yeah, in conductors. You have the equations as follows. You have del dot E equal to 0, del dot P equal to 0. And if I remember correctly, del cross E also remains same. Right? These three are left untouched. This because in conductor, all the free charge disappears, right? Even though you have a rho over epsilon naught, that rho stands for the free charges, whatever free charges you have in the conductor. But then if you have studied a little bit of conductors, you will realize that all the charge accumulates on the surface, and then there is no free charge that is there. Okay, so that's that. But the last equation is modified. Del cross B becomes mu epsilon dou E over dou T plus mu sigma E, where this sigma is the conductivity of the material, of the conductor that we're dealing with. And these mu and epsilon are relative permeability, and permittivity. I might have reshuffled the names, but yeah, roughly that's what it is. So your skin depth, D, I don't want to get too mathematical here, but is defined as 1 over kappa, where kappa again, it's proportional to, let's just say, mu epsilon and the frequency with which the light is traveling. So I'll just write it like this. And it depends on the expression goes something like this. Okay. Epsilon omega squared square root minus 1, and then the entire square root. And this, of course, is pi. And then you can get rid of this. Right? This is how you define your skin depth. And you see that it depends on the relative permeability and the permittivity of the respective medium that you're considering. And this is not only for the conductors, but any medium that you take. So yeah, I hope I answered your question. I digressed quite a bit.
Yeah, I got it. Thanks.
Yeah.
Yeah, I wanted to ask, you told that we can, in Griffith, I can look up the chapter which has interaction of light with matter, yes. But can you give me an overview? Why does light interact with matter?
Okay, why does light interact with matter is a question of quantum electrodynamics. Okay, and I don't really want to get into that. But the whole idea is there's this book by Feynman. Oh, okay, Alex, see you. Thank you for attending. Okay, so I'll give you like a very, very, very brief. This might again take time, but I'll try to explain it as the best I can. So if you have a surface, okay, let's just say a thin piece of glass, and you have light falling on it, all right, no matter how smooth your glass is, there are going to be holes in it. Okay, and this is an experiment that Newton also did in order to understand why do these light reflect, refract, and so on. Now, if this was a glass, what you would expect is that everything just passes through, right? We'll forget about what the angle of refraction, reflection, all of that is. It is supposed to pass through. But when you actually perform the experiment, if you had 100 photons coming in, only 96 of them pass through, but the 4 of them get reflected off. Right? And why this happens has to deal with the holes and the electrons or the atoms, let's just consider glass atoms that are present there. And why do they have to interact? That is a question of quantum electrodynamics, right? So if you are free, you can read up this book, QED, The Strange Theory of Light and Matter by Richard Feynman. I'm pretty sure all of you already are familiar with Feynman's books, Feynman's lectures, and so on. If you aren't, it's a very good book, QED. I read about this part just yesterday. That's why I was able to tell you what exactly is happening. But yeah, that's the rough idea. So why is there a partial reflection happening here and majority refraction happening here? That's an entire question of quantum electrodynamics. You'll have to understand how individual photons interact with individual electrons of the matter that they're going to interact with, that they're falling upon.
I would like to answer the question.
Sure, go ahead. Yeah.
So, if you wanted to know that how light interact with matter, then we have to consider light as a particle nature. Each particle is called photon. Whenever a photon, which is a packet of energy, then it gives electron the phenomena of absorption or emission. As an example, it is clearly explained in photoelectric effect.
Yeah, thank you. I couldn't see who that was. I'm sorry. Sorry, I didn't catch your name. Can you? Satyam. Okay. Satyam, thank you very much. Thank you very much. That was a valid answer, right? I mean, it does make sense. I mean, it interacts only if you can, if you treat your photons as particles and not waves, right? But the section in Griffiths that I told you about, where he talks about electromagnetic waves and about reflection and transmission and so on, they only treat electromagnetic waves as waves. So the photons that are coming in are only treated as waves. You don't even talk about photons, actually. You just talk about how the electric field behaves. You talk about field behavior rather than particle behavior. But if you want to actually understand what's going on at the absolute microscopic level, then yeah, you get into QED, and the entire book of Feynman deals with photons as particles. So the question of photons being waves doesn't even come in. So you don't have to even worry about it.
I have one question. If this is valid for glass also, means which don't have
It is
free
valid for
electrons.
every. It is valid for every material that you have in the universe, right? So if you read Griffiths, I think he also mentions a footnote about what exactly transparency means, and let me see if I can read it out for you. If I find it in time, he beautifully tells what exactly does it mean for a thing to be transparent, and it was based off a paper by, I believe, Hans Ohanian. Just a second. I hope that was Griffiths. Please, if I get it, then I'll send it to you. If I'm unable to tell it to you right now. But I should have read it somewhere here. Okay, if there's any other questions, I'll be happy to answer while I search for this at the same time.
Yeah, actually, so it means that the light is a photon or a particle or a energy packet which interacts with matter, right?
Light has dual nature, both particle and wave.
Yeah.
So if light does not interact with matter, then?
Okay, if light does not interact with matter, then
with the increase of amplitude and amplitude of a wave, the energy difference can be said. But the photoelectric effect explains that it is not the magnitude, rather it is the frequency of light that gives the energy of the individual wave. So that defined wave of visible in the electromagnetic spectrum has defined energy.
Yeah, that's correct. But I'm afraid, did you have a question, or were you just trying to, you know?
I mean, the purpose of my question is to, talk about dark matter because it doesn't interact with light.
Dark. Okay. I wasn't actually expecting that. But okay. Dark matters, if you assume dark matter is made out of particles, something that we haven't been detecting, then it would maybe interact weakly. I don't know if Sagar is here. Is he here? Because he has better hold on those topics than I. He's been researching dark matter more longer than I have been. But as far as my understanding goes, dark matter particles interact only weakly, even if they do. Right? That's why you have a class of particles called WIMPs, weakly interacting massive particles. Even though they are massive, they don't interact with stuff. And in order for light to interact with something, it must be electromagnetic in nature. Light only interacts with stuff that has some charge or can be charged, or that it can disturb a little bit. Like how, if you have let's say a piece of plastic. Okay, you have a piece of plastic. It doesn't it doesn't conduct electricity, or for that matter, it doesn't interact with electromagnetic field. It just sort of reflects everything that falls on it. But if you were to place it, I'm just giving you a very crude, vague, random example. Okay, it need not even make sense in real life, but I just want you to sort of imagine what is trying to happen here. Okay, so this plastic, which does not conduct electromagnetic waves, I'm talking about electromagnetic waves, it just pushes everything that falls on it. If you were to place it in a very strong electric or a magnetic field, the particles of plastic, the atoms that make up the plastic, sort of get disturbed from their equilibrium position, and there is a chance that they form dipoles. And if there are dipoles, if the applied fields are very strong, then there is a small possibility that your entire plastic sort of gets some amount of charge, right? Electric charge. And if that happens, then your electromagnetic waves, at least in this stupid example, can go through your plastic. It was a very, very, crude example, but I just wanted to get an idea as to how these things work. When you're talking about interaction of light with matter, any sort of matter, it has to deal with, it depends on what matter are you talking about, and it also depends on how exactly are you considering your light to be, right? So if you're talking about interaction with just glass or something, considering them as waves is more than enough. It's just electromagnetic waves, waves that have a perpendicular electric and magnetic field. That's more than enough. But then if you actually want to get down to further depth, if you want to zoom in further, then you'll have to start considering your electromagnetic waves as packets of energy, like someone mentioned out, the photoelectric effect and so on. That's when you'll have to start considering these waves as wave packets. But for the whole study of electrodynamics, right? For the whole study of electrodynamics, your gamma rays, your X-rays, your not cosmic rays, any spectrum of the electromagnetic radiation, for our purposes in electrodynamics as a whole, just electrodynamics as a subject, we are more than satisfactory to consider them as waves. That's enough for us. We don't have to get into the quantum nature of these waves, right? And one point to note again is when electrodynamics was formulated, when Maxwell gave his equations, light was, there was a debate obviously, but it wasn't proven strictly about the particle nature of light. Right? There wasn't concrete evidence until proper photoelectric effect came in. Even though there were double slit experiment only proved that light behaves as a wave. There was no concrete particle evidences until photoelectric effect, and photoelectric effect came up in the 1900s, whereas these Maxwell's equations, I believe, were somewhere in the 1880s or 1890s. So there is still that gap that occurs. And for our purposes, it works to assume these as just waves, right? So we're okay with it. And we don't have to worry about how these would interact at the microscopic level. And this wasn't dealt with until Feynman came in, right? Until they actually started looking into unifying all of these and see if they can be unified.
Actually, Newton's is also giving some corpuscular theory. I think he mentioned
Yeah,
that
but
light.
his was just like a what do you say? He just stated that, for this to make sense, light has to be corpuscular. He wasn't able to provide any concrete evidence as far as I know, right? I think he just theorized that it should be corpuscular.
I think that this is the base of photoelectric effect. Means Einstein take the base of this Newton's theory.
Then I'll have to read up again. I might have not read it.
Yeah, I've read that. Means this is the base of Einstein photoelectric effect.
Okay, but I don't think Newton was able to concretely prove that the light was particle in nature, right?
Yeah. He is not able to.
Right. Yeah. Okay. Yeah. So
As much as I know, Newton's corpuscular theory was light when passing through a prism splits into different colors. And when it again process that after crossing the prism, it unites. So he said that light is have a corpuscular nature. But Albert Einstein didn't take Newton's corpuscular. So he rather takes Planck quantization condition to explain the photoelectric effect.
That's what I remember reading. As in, Einstein was trying to prove the quantization of these photons. But that's again a fun topic to discuss later. But are there any other questions related to today's session? Since we're also running out of time, it's almost dinner time. So any other question that I can help you guys out with? Okay, so I'm assuming there's nothing. All right.
Sir.
Yeah, go ahead. Sorry, did someone just unmute and talk? I'm sorry.
Yes, sir. I told that there is no question now, sir. Thank you.
Okay, yeah, right, yeah, okay. So if there are no questions, then thank you for joining in today. I hope you had fun learning about electrodynamics. I tried to explain it the best way I could, and try to make it as little mathematical until the last part. I hope you had fun, and tomorrow in the neutrino group, we'll be talking about relativistic kinematics. We'll see how particles behave when they move at relativistic speeds. I think the topics we'll be covering are roughly, let me tell you what we'll be covering tomorrow. It's a little bit of special relativity, of course. And yeah, maybe tomorrow we can see how electric and magnetic fields are, the same, two sides of the same coin. I won't be getting into a lot of special relativity tomorrow, but we will, briefly see what the Lorentz contraction is, what the twin paradox is, and we'll look at Lorentz transformations. We'll look at how coordinates transform, and yeah, we'll get into a little bit of next level of vectors called the four vectors, and we'll see how how the momentum changes for a particle that is moving at relativistic speed and so on. Right, so if you're interested, you can join in tomorrow. I think the Zoom link is going to be the same. And the timing you will know if you just check out the Discord channel of the neutrino group. So thank you for joining in. Have a nice evening. Have fun.
Yeah, it is a very nice interactive session.
Yes, sir. Thank you, sir.
Thank you.
Thank you very much.
Hey everyone, just 1 minute. Vikram, thank you so much for the wonderful session. I think the gamma ray group from tomorrow, the electromagnetic group, will be focusing on the refreshers for programming. Tomorrow will be Python, and day after will be Pandas, if I'm not wrong. So those of you in the electromagnetics group, we are predominantly picking from this batch for the solar physics project. So if you feel you know Python pretty well and you're confident, now is your chance to kind of contribute and teach a little bit. So just put it on the group itself. you can just put it on the gamma ray group saying, hey, I'm confident in this particular topic and I would like to teach. And we'll see if there are a lot of people, we might have to stick to maybe 5 or 6 different presenters. So for both Python and Pandas, you can come forward and just let us know what your skill sets are and we'll take it from there. And yeah, like he said, his 6:30 session tomorrow, Vikrant will be covering relativistic kinematics. So if you're interested, you can join that as well. Okay, that's it from my side. Thank you so much, guys. Hope
Yeah, ma'am.
day
Thank
2
you.
yeah, bye.
Thank you, ma'am.
Thank you, ma'am.